Today we're going to master hybridization by looking at some practice problems. Before we start, we need to define a critical concept, the electron domain, which is any area where there's a significant amount of electron density. There's two main types you need to recognize: bonding domains and non-bonding domains, also known as lone pairs. Remember a very important rule: whether a bond is single, double, or triple, it still only counts as one domain because all the shared electrons are concentrated in the same general area. So let's look at an example using hydrogen cyanide, or HCN. If we focus on the central carbon, you can see it is surrounded by two electron domains: the single bond to hydrogen and the triple bond to nitrogen. Because there's two domains that want to be as far away as possible, they create a linear shape with a bond angle of 180 degrees. To determine hybridization, we use the total number of electron domains around an atom. So looking at this chart, we can look at the relationship you should memorize. 2 domains gives us sp hybridization, 3 domains gives us sp2 hybridization, 4 sp3, and if we go even higher to 5 domains or 6 domains, you get sp3d hybridization and sp3d2 hybridization. Keep this table in mind because I want you to find the hybridization of carbon number 2 in the next molecule. Take a look at this molecule and focus on the carbon labeled with the red 2. To find its hybridization, count the areas of electron density that are surrounding it. It has a single bond that's connected to carbon 1, a single bond connected to carbon 3, and there is a double bond that's connected to the oxygen. Since the double bond only counts as one domain, carbon 2 has 3 electron domains. And this makes it sp2 hybridized. Next, let's switch gears and find the hybridization of the oxygen atom in this molecule. Looking at the structure, acetaldehyde, oxygen has a double bond to carbon, and it has 2 lone pairs. Following our rules, the double bond is one domain, and each lone pair is its own domain. Now this is going to give us a total of 3 electron domains. Referring back to our table, the 3 domains means that the oxygen is also going to be sp2 hybridized. Now let's look at a more complex structure and find the hybridization for nitrogen atoms A and B. Look closely at the bonding and remember to account for lone pairs that might not be drawn but are necessary for a neutral nitrogen atom. If you're unsure whether a particular atom has lone pairs, calculate its formal charge. Formal charge compares the number of valence electrons an isolated atom normally has with the number of electrons assigned to that atom in the Lewis structure. For instance, if the formal charge is 0, the number of electrons assigned to the atom in the Lewis structure must equal its normal number of valence electrons. If the electron count does not match the atom's normal valence electron count, the atom will have a formal charge. Now, nitrogen has 5 valence shell electrons. However, both nitrogen A and B only have 3 electrons assigned to their Lewis structure. We must then add a lone pair so that they have the 5 valence shell electrons that they'll need to complete their octet. Let's get back to our example. So for nitrogen A, it's connected to 3 different atoms by a single bond. Including its lone pair, it has 4 electron domains, which corresponds to our sp3 hybridization. Now for nitrogen B, it's part of a double bond, so with the double bond being one domain and the single bond being one domain, its lone pair is also one domain, so it has a total of 3 electron domains, making it sp2 hybridized.